So here is a distribution that shows all values between 0 and 20 are equally likely. I prefer real-life applications. This one doesn't have any story associated with it, but the story that I often like to make up is about a bus. So if you look at your worksheet on page 3, you'll see buses arrive at my stop every 20 minutes. My wait time could be uniformly distributed between 0 and 20. So I could get lucky and arrive just right when the bus arrives and have 0 waits. Or if I arrive right after the bus leaves, I could have a 20-minute wait. And again, this is based on the assumption that the bus comes every 20 minutes to my bus stop. Now, you might be wondering why we have 1 over 20 right there. That is a good question. Let me hop over to the worksheet. The probability density function is f of x is equal to 1 over b minus a for values of x between a and b. If x is uniformly, we write x distributed u parentheses a comma b, where a is the lowest value of x and b is the highest. So x in our case is distributed uniformly from 0 to 20. We just give the endpoints. And then in our case, f of x is equal to 1 over 20 minus 0. And that's just going to be 1 over 20. And the reason that that is 1/20th, isn't that the same as 0.05? The reason it's 1/20th or 0.05 is just to force this entire area to be 1. Because if we do length times width, the length of this rectangle is 20. The width of this triangle is 0.05 or 1 over 20. And if you take 20 times 0.05, you're going to get 1. And so that meets the criteria that we have a total area under the curve of 1. So the total probability is 100%. And that's why we have a fraction for the height of our rectangle. So what is the probability that I wait exactly 10 minutes? Here's my 10-minute location. So I can draw a line, represent that exact wait time, and then the probability that x is equal to exactly 10 will be 0. It's quite possible that I'll wait 10 minutes and 5 seconds, or 6 seconds, or 6.3 seconds. So the likelihood of any specific value is 0. What is the probability that I wait less than 10 minutes? Well, you might be able to guess that it's 50%. You can just do that kind of intuitively. Or you can say, I'm going to do length times width. So shading that area that we're talking about is, the probability is area, and it's length times width. So it would be, the length is 10 minus 0, and the width is 1 over 20. And so that's going to be 10 times 1 over 20, and that's going to be 1/2. 10 over 20 is a half, so 0.5. What is the probability that I wait between 0 and 20 minutes? Well, that's going to be 100%, or just 1. Okay, so that is just one example of a uniform distribution. Here's the more official theoretical information in the box. If x is distributed uniformly, This is the notation, just like we had the Poisson distribution and the binomial distribution. So we're adding to our collections of distributions. Next up, we'll learn about the normal distribution. So the probability density function is f of x is equal to 1 over b minus a. If you didn't come from Math 111, this might be new notation to you, but another way to say it is just y is equal to 1 over 20, or y is equal to 0.05. So that's just going to be the horizontal line that helps to define that box. So this tells you how wide or how tall the box is. Now, with this distribution, we have a formula for the mean and a formula for the standard deviation. And we actually had formulas for the mean and standard deviation with Poisson and with the binomial distributions. So we're just following with that tradition. The mean of the uniform distribution is the midpoint. You just take a plus b and divide by 2. So the mean in this case is the midpoint of the rectangle. And the sigma formula, take b minus a, square it, divide by 12, and then take the square root. And sometimes students ask me where that 12 came from, and I don't remember where it came from. I just call it good. It's part of the formula. And I think if we did some calculations and derived this formula, we would see where it came from. But don't worry, there's not a secret meaning to that I'm hiding from you. Okay, so let's make up another little story here. Let's say that my students' ages are uniformly distributed between 15 and 45. Now, I do not have any 15-year-olds. I probably have some 45-year-olds, and I do not actually expect to have a uniform distribution of ages in my class. All ages are not equally likely. But let's just pretend this is true for the sake of this problem. If x equals student ages, write the correct notation for how x is distributed. So we write our x, squiggle represents distributed, u for the uniform distribution, that's a capital U, and then we just say 15, comma, 45. So that's my a value, and that's my b value. Draw a graph of the distribution, label both axes with variables and numbers. Okay, so I'm going to draw my x-axis here, my y-axis, and the student ages is what x represents. So I will put 5, 10, 15, 20, 25, 30, 35, 40, 45. Trying to scale it consistently. And this said to label both axes. So I have labeled the horizontal axis, but how do I label the vertical axis? And I also need to show that rectangle representing my uniform distribution. So there's my rectangle, goes from 15 to 45. I don't have students over here. The height of this rectangle is going to be different this time. Basically, it's going to be 1 over b minus a. Here's my a, here's my b. b minus a is going to be 30, which means that this rectangle is 30 units wide. So that's the width of the entire rectangle. So this needs to be 1 over 30. That way, I still force the total area to be 1. So that's why we always make this 1 over the width of the rectangle. That forces this total area to be 1. Now I'm not shading it yet because here comes a question. What is the probability that x is greater than 19? So I'm going to draw a line, change colors here, draw a line. Let's see, this was going by 5s, so 19 would be approximately there. 20 was where that blue tick mark is. I'm going to shade this area to the right. So that should be the majority of my students. I'm going to guess like 85–90% maybe. But I can find the actual percentage by doing length times width. So the probability is equal to the area, which is equal to length times width. So how long is that rectangle? 45 minus 19. The red part only goes to 19. And then times 1/30. So that 45 minus 19 is going to be 26. So 26 times 1/30. 26 times 1 divided by 30. 0.8666. So 667. Or we could say, well, that's actually fine. I forget what your online homework requires. It may want 4 decimal places like this. I often only want 2 decimal places. So then it would be 0.87 for me. But pay attention to your online homework and what it requires. And I believe we have one more page, so I'll just cut this off here.